Hi everybody, in this video I'm going to go over 9.3.1 study section where we're going to discuss magnetism. So we already know some things about magnets. We know that they have a north and a south pole, and we know that if we have a north and south pole next to each other, they're going to attract. And that's because opposite poles attract. Now if we have a south and a south, or a north and a north next to each other, they're actually going to repel, and that's because the same poles repel. And this is something we already know from our experience together in the classroom. Now, we want to be able to measure the force that a magnet exerts, and one way of you doing that is to use a compass. So I'm going to go over to the simulation where we have compasses. So here we have all these compasses. And what a compass is it's a tiny magnet where the red end is our north and our white end is our south. And it allows us to see the direction of the force that a magnet is exerting. So we can see here that the red ends of the compass point away from the north end of the magnet. And if we look at this, we can see sort of a pattern emerging where these red ends are pointing away from the north and then up and into the south. And we can attach all of these compasses into this loop that points out from the north and into the south. And we can do the same thing on the other side when we find another loop forms that goes out from the north and into the south. And we get even bigger loops as we go further away, but they're all going out from the north and into the south. And what this shows us is that a magnet has a field. It creates a magnetic field similar to the way that the Earth creates a gravitational field or that a charge creates an electric field. Magnets create a magnetic field. And these magnetic fields can be represented by using magnetic field lines. And these field lines form these loops that we see. And they go out from the north and into the south. And these loops do not intersect. They form loops out from the north into the south. So if I get rid of this, we can see this more neatly. This is what our magnetic field lines look like. Another way of visualizing these field lines is to use iron filings. So let's go to a different simulation that can show us this. So here we have a bar magnet, has a north end and a south end, and what they've done is they've sprinkled iron filings on top. This works because iron filings are magnetic, so they spread out due to the force that the magnet exerts on them, and they form these lines that we can see here. And you can see that this follows the magnetic field lines we've already seen. They go out from the north and into the south. Okay. And we can also look at this where we have two opposite poles next to each other. And we see again, it forms this sort of circle, this loop from the north to the south. It will look different if we have two of the same poles next to each other. You can see that the field lines sort of bend away from each other in this case. So if we want to visualize field lines, I have a picture here for us. We see that they form these loops that go out from the north, loop around and into the south. If they have opposite poles next to each other, the field lines loop towards each other. And when we have the same pole next to each other, the field lines move away from each other. So this is what it looks like. So I want to go through a couple quick properties of the magnetic field lines. So we know a couple things about magnetic field lines. First, we know that they show the direction of the magnetic force. We also know that they point from north to south. We know that they never cross. but they form loops. And we know that a tiny magnet, like a compass, will align itself with the field. So these are the properties of magnetic field lines I'd like you to know. Another interesting thing about magnets, if we have a large bar magnet, it will have a north and a south pole. If we hit this magnet with a hammer and we try to divide it up, you're not going to get one north and one south. Instead, you're going to get two new magnets that each have a new north and a new south. So why is this? Well, what a magnet is it's caused by all of the atoms in the magnet have their charges aligned in a particular direction. Okay? And that's why it stays magnetized, because all of these atoms are lined up in a particular direction. So if you split it in half, the atoms are still lined up in that direction. So you just end up creating a new north pole and a new south pole because the alignment of these charges in an atom. So you can never get just a north pole or just a south pole by itself. If you break it in half, you're just going to get a new north and a new south. If you broke it in half again, you get a new north and another new south. So this is an interesting property of magnets. Okay. So the last thing that we want to talk about with magnets is that you can induce a magnet using a permanent magnet. So this is a bar magnet. A bar magnet is a type of a permanent magnet. Okay. And it's a permanent magnet because, like we said, all of the charges in that atoms in the magnet are aligned in a particular direction. But if we have something else near it, let's say we have a paper clip, what happens is all the charges in a paper clip will start to align themselves as well. If they're right next to the magnet, the charges inside the paper clip will start to align themselves also. And as a result, you're going to get something of a north pole on one side and something of a south pole on the other. And this is called an induced magnet. What an induced magnet is if you have a piece of metal that you store next to a magnet, the charges in the metal, in the atoms in the metal, will align themselves and produce this temporary magnet. So for a little while, this paper clip might attract other paper clips, but after a while, all of the charges will go back to normal and it will no longer be a magnet. All right, one last thing. The Earth itself has a magnetic field. You might have heard of Aurora Borealis, and that is because of the Earth's magnetic field. So let's talk about that for a quick second. All right, so this is the Earth, and the Earth has a magnetic field. So the reason why compasses work is because they're aligning themselves with the magnetic field. So if we imagine we're here and we have a compass, the compass we know is going to point up as north and down as south. So the north end of the compass is pointing up, the south end of the compass is pointing down. But if we really start to think about this, we see something unusual. We know up here is the geographic North Pole. Right? That's where Canada is. And down here is the geographic South Pole. However, if we look at our compass, our north end of our compass is pointing up. It's pointing up because it's being attracted to the south end of another magnet, which is our Earth. So that means the south end actually has to be up here. And the north end has to be down here. So what actually happens is the South Pole, the magnetic South Pole, is located at the geographic North Pole. And the magnetic North Pole is located at the geographic South Pole. And we know this because the north end of our magnet has to be pointing towards the south end of our Earth. The south end of our magnet or compass has to be pointing towards the north side of the Earth. So this is sort of confusing, but the geographic North Pole is actually where the magnetic South Pole of the Earth is located, and the geographic South Pole is actually where the magnetic North Pole of the Earth is located. And this is the last key idea I want you to know, that these are switched. So the Earth's geographic North Pole is the magnetic South Pole, and Earth's geographic South Pole is the magnetic North Pole. Okay, so this is everything I want you to know about magnetism for now. I want you to know what ends of magnets attract and repel. I want you to know these properties of magnetic field lines and how to visualize them. I want you to know that if you break a magnet in half, because of the alignment of the charges in the atom and the magnet, you're going to get two new magnets. You can't get a North Pole or a South Pole by itself. I want you to know if you have a permanent magnet and a piece of metal next to it, you can induce a magnet temporarily. And I want you to know that the geographic poles and the magnetic poles of the Earth are opposite. Hopefully that clears up your understanding of magnetism. Please let me know if you have questions.